Today we're going to learn about base equilibrium, that would be for weak bases, and the relationship between Ka and Kb and some other stuff too. We'll learn about buffers and acid-base properties of salts. So when we have a weak base, the equilibrium constant would be a Kb, B for base, and here are our generic reactions. These would be bases. These would be the acids. This is really the same reaction. It's just that this is for, oh shoot, the molecular base. Yeah, this one's for a molecular base. Here's a generic reaction for a base that would be an anion. Okay. And the Kb is just products of a reactants, products of a reactants. The important thing, this is the most important thing right here. This Ka times Kb is 10 to the minus 14. So if you have a Ka, you can find the conjugate base Kb through this equation. And here are some Kb values that you might need for homework assignments. Okay. Another important note, when we have a base that's an anion, we write the base as a sodium salt of the anion. So we'll have the sodium ion with the anion, and whenever you have a cation and an anion, we call it a salt. So we will ignore the sodium ions and just look at the anions when we're talking about the base equilibrium reactions. So first problem, write the hydrolysis reaction and calculate the pH of 0.5 molar sodium acetate. And you're given the Ka for acetic acid, which notice this is the conjugate acid for acetate, the base. So try to write the reaction. I've got the reaction right underneath here. We're going to ignore the sodium. We will have the acetate ion plus water, make the conjugate acid and hydroxide. Here's your reaction. Oops, hold on. All right, there's the reaction. Okay, now we have our reaction. We're going to set up an ice box. We know that initially the acetate is 0.5 molar. Everything else is 0. Acetate will go down, acetic acid and hydroxide go up. And final, we just add the two I and C rows. Or equilibrium, we add the I and C. Now, notice this is a base reaction because we have a base with water, and we only had the Ka for the conjugate acid, so we will use this equation right here to get the Kb. You can do it yourself, pause, or here we go. So Ka times Kb is 10 to the minus 14. So I solve for my Kb, and there I have it. And now I will do products, x squared, over the reactants, 0.5 minus x, is equal to the Kb. Now Kb is so small, that means products are really small, which means x is really small, means it's so much smaller than 0.5, that I'm just going to assume that 0.5 minus x is approximately 0.5. Which gets us right here. So I start here, I make my assumption, I multiply both sides by 0.5, and I get x squared is 2.8 times 10 to the minus 10, take the square root of both sides, find x, and now recall x is hydroxide right here. It's not H plus as in the Ka problems. So x is my hydroxide concentration. I can get the POH, negative log of OH. There we go. There's my POH. Now my pH is just 14 minus the POH. And there you have it. Oops. Next topic, acid-base properties of salts. Now salts are just ionic compounds. We check the positive and the negative ion to see if they are acidic, basic, or neutral. And here are your rules. Anions, the negative ions. You check the conjugate acid of the anion. If the conjugate anion is weak, if the conjugate acid of the anion is weak, then the anion is a base. If the conjugate acid of the anion is strong, the anion is neutral because the anion, if it were to try to take on an H+, it would just split back apart immediately, so that anion is not at all basic. It doesn't attract H+, it cannot accept a proton. Remember, bases accept protons. If an anion takes on a proton and then splits apart because the conjugate is strong, then that anion is not a base because it won't take on a proton. Cations, they're all acidic except the alkali and alkaline earth metal cations. So all cations are acidic. Anions, you check the conjugate acid to see if they are acidic or basic. Let's do some problems. There is one thing, there's something called amphiprotic that I haven't mentioned. If an anion has an H in it, then it actually can be acidic if the anion's H can come off. So anions can be acidic if they have an H in them that is ionizable. We won't worry about that so much. Okay, sodium nitrate. We need to figure out if this is acidic, basic, or neutral. Well, we have to first check the anion and the cation. So we have Na plus is the cation. Let's look at our cation rules. They're all acidic except alkali, alkaline earth metals. This is an alkali metal. So this is it's not acidic. Not acidic. And cations are never basic, so it's neutral. So the Na plus is not going to do anything. Nitrate, NO3 minus. What do we do with anions? We have to check the conjugate acid. Let's do that. The conjugate acid is HNO3. What are we supposed to do with those? Let's see. If the conjugate acid is weak, is this weak or strong? Hibber, hickel, high, hono, hickelo, H2SO4. This is the hono. This is a strong acid. Therefore, nitrate is, let's see, what does it say? If the conjugate acid is strong, the anion is neutral. This was strong. The conjugate was strong, therefore this is neutral. Therefore, sodium nitrate is neutral. Neutral. Not acidic or basic. Okay, next problem. We have Na plus, which is an alkali metal, which is neutral. Cations, always acidic unless they're an alkali or alkaline earth metal. Then we check our nitrite, NO2 minus. Anions, check the conjugate acid. Let's see, HNO2 is the conjugate acid, which is a weak acid. Let's read our instructions again. If the conjugate acid of the anion is weak, HNO2 was weak, the anion is a weak base. Okay, this is a weak acid, therefore nitrite is a weak base. Therefore, NaNO2 is basic. Now, did I tell you to write a reaction? Yes. If the salt is acidic or basic, write a reaction showing this. So when you write a reaction, you take whatever was acidic or basic, you add water to it, and you figure out what you're going to form. So I want you to pause, because the answer is sitting here, but I want you to think about it, try to figure it out. And here's your answer. You get the conjugate acid and hydroxide when you have a weak base. Okay, next problem, number 3. Again, we have sodium ion, which is an alkali metal, which is neutral. So far, so good. Then we have acetate, and with anions, what do? We check the conjugate acid. And the conjugate acid is HC2H3O2. Is that a strong acid? No, it's not on our list. That is a weak acid. And it turns out that anions whose conjugates are weak, if the conjugate acid of the anion is weak, the anion is a weak base. So, therefore, acetate, C2H3O2 minus is a weak base. I have to write a reaction. And the reactions, we always take the weak base, not the neutral thing. We're not going to worry about our neutral thing. We take whatever was weak, we add water to it, and you figure out your products, and the answer is right below here. So pause, figure it out on your own. Here's your reaction. Okay, aluminum chloride. Now this one is tricky. Al3+. Cation is not an alkali metal. It is not an alkaline earth metal. Therefore, it is acidic. Cl-, anions. Check the conjugate. Conjugate acid is HCl, which is a strong acid. Therefore, Cl- is neutral. So this thing overall is acidic. And now I have to write a reaction. This is a kind of reaction you cannot possibly predict. You've never seen this before. These are called complex ions. When we have Al3+ in water, it does not exist as aluminum 3+. It exists as aluminum 3+ with 6 waters attached to it. The number of waters attached to the metal typically will be 2 times the cation's charge. Okay, so the cation's charge was +3. Therefore, we will have 6 waters. That's just a rule. Okay, now when we put this into water, recall that acids give off protons and bases accept protons. So this acid, this is an acid right here, we're going to give off an H+. And we'll give off an H+ from one of the water molecules. So we get a funny looking thing. We're going to have an aluminum. We're going to take off one of the waters. Okay, so we only have 5 waters left. And one of the waters loses an H+. So what's left? If I have an H2O and I take away an H+, what do I have left? Hopefully you got it. You have an OH- left. And now we have to figure out what the total charge is. We started out with a charge of +3. So now my charge, I took away an H+, I'm only left with a +2 charge. So that's one of my products. The other product that I have is, recall I took an H+ from one of these waters, and I'm going to transfer that H+ to the water that I'm reacting with the aluminum complex ion. So now I have an H3O+. And I'm showing that this complex ion right here is acidic because I produced acid. All right, so I cleaned that up a little bit so that you can see the overall reaction again. Whoa, I'm on the wrong thing. Here we go. Ah, what just happened? Hold on. Okay, there we go. There's your overall reaction. Okay, KCN. K+ is an alkali metal, which is neutral. Cn-, conjugate acid is HCN, which is a weak acid. Therefore, Cn- is a weak base. It's basic. Now you have to write a reaction for Cn-. Oh, overall this whole thing is basic. Write a reaction for Cn- with water producing hydroxide, because things that are basic should produce hydroxide. Pause or look at the answer now. Here we go. There's a reaction showing that we have a basic substance. Okay, last one. Fe2+. I figured that out because this is 2 and I have nitrate is -1. Fe2+. It's not an alkali metal, alkaline earth metal, therefore this is acidic. Nitrate, NO3-. We did that one earlier, but let's do it again. Conjugate acid is HNO3, which is a strong acid, therefore nitrate is neutral. Neutral and acidic overall. This salt is acidic. Now let's write the reaction. Let's see if you can do this on your own. We take our Fe, it's +2, so how many waters? Rebecca, call it out. How many waters? She left. We're going to have 4 waters because the number of waters will be twice the charge, 2 times the charge of the cation. And then we add a water. This is a reversible reaction. This piece right here is called a complex ion. Complex ion. Okay, acids donate protons. So we're going to strip a water off of that complex ion. And so we have 3 waters left. And the water that we took off, we're not taking it off actually. We're only taking off an H plus from the water. So think about what are we left with? We're left with an OH. And the charge, before my charge was +2 and I took off an H plus, I took away 1, so I'm left with a +1 charge. And that H plus transfers over to the H2O. I have an H3O plus. And there you have it. Hold on. Okay.
Now we're going to do 17.2 buffer solutions. What's a buffer? Well, it is a solution containing both a weak acid and a weak base that can resist changes in pH upon addition of a strong acid or strong base.
So here's some examples of where buffers exist in nature, like in every human being, in every mammal. Blood. Our blood is buffered with a phosphate system. Many of us take buffered aspirin when we get older because our tummies get very, very sensitive to the acidic aspirin that we take. So try buffered aspirin. Extra strong. Bufferin is called bufferin. You probably never knew this. It's called bufferin because it's buffered aspirin. I'm making girls laugh. Isn't that funny? And over here we have pond master. Did you know that if you have a pond with fish in it, you have to make sure that the pH stays right so that your little koi fish can survive properly? So buffers are all over nature. They're all around. How does it work? Well, strong acids dissociate completely and they make H+. Strong bases dissociate or ionize completely. They make hydroxide. When you add a strong acid to the buffer solution, the weak base, A-, will react with the H+ from the strong acid and produce your weak acid. So it's kind of like Le Chatelier, although this reaction goes all the way to the right, pretty much. All of your H+ gets used up, makes the weak acid HA. And what about when we add a strong base, hydroxide? Well, hydroxide will react with the weak acid that was in the buffer to give us a weak base and water. Okay, notice I just changed the arrows. So if in your notes you have a single arrow, you should switch that to, if you have a double arrow, switch that to a single. These reactions go to completion for these buffer systems. So let's do a problem. Here's a buffer system. Oops. And I want to know if I had HCl, what's going to happen? First, recognize the HCl is going to react. It's a strong acid. Let's figure out the HCl first. The strong acid will react with the weak base. We don't care about the Na here. We just care about the C2H3O2-. So it'd be the H+ from the hydrochloric acid with the C2H3O2-. And if you can figure it out, write it down. But here it is. Okay. If we add hydroxide, sodium hydroxide, all we care about is the OH-. Hydroxide will react with the acid, and here's what you get. There you go. So the weak acid with the hydroxide, you get the conjugate weak base and water. Makes the pH change by very, very little. Okay. Now you try this one. We've got ammonium nitrate. Ammonium is our acid, ammonium ion, NH4+, and ammonia, NH3 is the base. So if we had an acid, H+, it reacts with the base, NH4. Write it down if you can figure it out. Pause. There you go. If we add hydroxide, remember that reacts with the NH4+, the weak acid. And we will get, we get back our weak base and water. Okay, last thing, solving for the pH in a buffer system. This is easier than the Ka problems or the Kb problems. Super easy. You write up a normal, regular old ice box. But this time we have both the acid and the base present. Our arrow would be right here. I just couldn't get it in there with this particular software. I probably could. I just pretend this arrow is sitting there and draw one in. Okay, now we're going to assume, what do you think we're going to assume? X is much smaller than 0.25. And we have our Ka, which would be products, 0.25 times x over 0.5. We got rid of the minus x and the plus x. We solve for x, which is, notice the H plus. Take the log. Gives me my pH. All right, next problem. These are super easy. We have acetic acid and acetate. We write, because we have a Ka, we write the acid reaction. These are not reacting with each other. This is the reactant. This is a product. The biggest mistake students make is to put both the weak acid and the weak base as reactants. One is a reactant. If you have a Ka, make the acid a reactant. If you have a Kb, make the base a reactant. So there's my reaction with an arrow right here. And I fill in my initial concentrations, very straightforward, just like the problems we've been doing in class. Here you go. And we just take the pH, which is negative log of x, which is this number, and we get the pH. And that's it.